Have you ever wondered what the future of space travel might look like? Will we be hopping from planet to planet as easily as we travel between cities today? Imagine a universe where interstellar travel is as common as a road trip, where the vast cosmic distances are conquered not by brute force but by the power of quantum physics. This is no longer a mere science fiction trope, but a tangible reality within our grasp, thanks to quantum-accelerated spacecraft propulsion. Quantum-accelerated spacecraft propulsion is poised to revolutionize the way we explore the cosmos. It's a game changer, a paradigm shift that has the potential to take us to the farthest corners of the universe. This is a technology that pushes the boundaries of what we thought was possible, and it's all based on the cornerstone of a pivotal mathematical formula, the McGinty Equation. The McGinty Equation is no ordinary formula. It's a complex blend of quantum field theory, fractal mathematics, and gravity. It's a formula that optimizes propulsion systems, making space travel faster and more efficient. With it, the universe becomes less of an uncharted wilderness and more of a navigable ocean. The equation itself, piece at xt, equals sign piece qft xt plus piece fractal xt dmqs, might seem intimidating at first glance, but don't let the sea of symbols deter you. Each component of the equation plays a crucial role in the magic of quantum-accelerated propulsion. The piece qft xt is the solution of the free quantum field theory, while piece fractal xt dmqs represents the fractal structure of the universe. And then there's the gravitational force, the g in the equation, which represents the perturbative effects of gravity on the quantum field. In the grand scheme of things, the McGinty Equation is our compass, our map, our guide to the cosmos. It's the key to unlocking the future of space travel, a future where the stars are no longer out of reach. To understand the future, we must first delve into the McGinty Equation. The McGinty Equation might seem daunting at first glance, but let's break it down. Dive into this sea of symbols and variables, and you'll find it's not so intimidating after all. The McGinty Equation, or MEQ as we'll call it, is essentially a sum of two components. The first, piece qft is the solution of the free quantum field theory. Imagine it as the basic rhythm of the universe, the underlying wave pattern that describes how particles like the protons and electrons we learned about in school behave and interact. The second component, piece fractal XTDMQs, is a bit more complicated. This is the fractal correction term. The fractal here refers to a self-similar pattern, something that repeats itself at different scales. Think of a snowflake, or the branching of a tree. This term corrects for the fact that the universe isn't just a simple repeating pattern, but has complexity and structure at every level. This fractal correction term is derived using a trio of mathematical tools: integral calculus, the Laplace transform, and the convolution theorem. These tools allow us to handle the complex, layered reality of the universe. Now, why is all this important? It's because understanding and applying the MEQ is key to optimizing propulsion systems. With it, we can make spacecraft propulsion more efficient. We're talking about the difference between a leisurely stroll in the park and a high-speed bullet train. This could mean reaching distant planets in a fraction of the time it currently takes. The MEQ isn't just a set of symbols and variables on a page. It's a roadmap to a future where the farthest reaches of our solar system and beyond are within our grasp. It's a key to unlock the door to a new era of exploration and discovery. While the equation is complex, the goal is simple: faster and more efficient space travel. The McGinty Equation didn't stop evolving. In fact, it was modified to account for the effects of gravity. Consider this. We've got the original McGinty Equation piece xt equals sign piece qft xt plus piece fractal xtdmqs, where piece qft xt is the solution to the free quantum field theory, and piece fractal xtdmqs represents the fractal potential of mechanical systems. But as we discovered, the original equation was not enough to account for all the nuances of space travel. Gravity, that invisible force that keeps us tethered to Earth, has a significant impact on the motion of celestial bodies and spacecraft. It's a force that can't be ignored when we're talking about space travel. So, the McGinty Equation was modified to include the gravitational force. The modified equation, piece xt equals sign piece qft xt plus piece fractal xtdmqs plus piece gravity xtg, now includes a term piece gravity xtg that represents the perturbative effects of gravity on the quantum field. The g in this term is a parameter that characterizes the strength of the gravitational force. It's essential because it allows us to account for the force of gravity while planning our space voyages. Without it, our calculations would be off, and we could end up light years away from our intended destination. The fractal potential term Vyt has a self-similar fractal structure, which is described by the constant parameters V0, L, and S. The fractal correction term can be derived using integral calculus, Laplace transform, and the convolution theorem. This is a crucial part of the equation, as it helps us understand the intricate patterns and complexities of quantum field theory. The modified McGinty equation, combined with general relativity, represents a significant leap forward in our understanding of quantum field theory and its applications in space travel. It opens up new possibilities for faster and more efficient travel to distant planets and beyond. With the inclusion of gravity, the McGinty equation became even more impactful in the realm of space travel. Now that we have broken down the McGinty equation and its modifications, we can see how it fits into the bigger picture. The future of space travel is being shaped right now as we speak, and it's quantum accelerated. The McGinty equation, in its original and modified forms, is the mathematical backbone of this thrilling development. This equation, with its intricate components, optimizes propulsion systems, making them faster and more efficient. Imagine a spacecraft, powered by this quantum acceleration, zipping through the cosmos, reaching distant planets and even galaxies that were once thought unreachable. This isn't just about speed, though. It's about efficiency, about sustainability, about pushing the boundaries of what is possible. It's about exploring the unexplored, venturing into the unknown, and making the universe our playground. And all of this potential, all of this promise, is contained within the neat mathematical package of the McGinty equation. Quantum accelerated spacecraft propulsion, powered by the McGinty equation, may very well be the key to unlocking the next chapter in our space exploration saga.